Welcome to this explainer. Okay, today we're doing something a little bit different, and honestly, I am so incredibly excited about it. Instead of just staring at standard photographs, we are going to use our mental whiteboards. We're going to sketch out 9 highly precise tools used for measuring, well, seemingly invisible gaps in engineering and mechanics. We are talking about feeler gauges. These are totally the unsung heroes of precision. By visualizing these tools from the ground up, we'll understand not just what they look like, but exactly how and why they're engineered the way they are.
So let's dive right in. Do me a quick favor. Just close your eyes for a second. I want you to imagine a tool designed to measure spaces so incredibly tight, so microscopic that a single human hair couldn't even slip through. I mean, how do you measure empty space when you can barely even see it? You obviously can't stick a ruler in there, right? A tape measure is completely out of the question. You actually need something that physically occupies that exact microscopic void.
Just to make sure we're all on exactly the same page before we start drawing up our blueprints, a feeler gauge is exactly that. It's a precision instrument that traditionally looks a lot like a metallic deck of cards fanned out. Each card, or leaf as they're called, is machined to an unbelievably specific thickness. And the idea here is just brilliant in its simplicity. You just keep trying to slip different leaves into a tiny space until you find the one that fits perfectly, with just the slightest little bit of drag. Once you find that perfect fit, you look at the number printed on the leaf and boom, you know exactly how wide your invisible gap is.
To keep our mental sketch organized, we are going to cover 4 main categories today. First, the classic blade shapes. Second, the metric versus imperial systems. Third, double-ended and wire configurations. And finally, precision blocks and digital setups.
All right, starting off with Section 1, the classic blade shapes. Let's mentally sketch out the foundations here. These are the shapes you're going to see most often rolling around in a mechanic's toolbox or on a machinist workbench. So, if we were standing at a whiteboard right now, here is exactly how you'd sketch them. For gauge number 1, you draw a standard metal fan, your classic leaf type. Give it a sturdy, rounded silver handle at the base and mentally engrave the words stainless steel right into it. From that pivot point, a beautiful, uniform array of silver leaves fans outward, and each one is stamped with its precise thickness, like 0.04 or 0.05. Now, let's contrast that with gauge number 3. Erase that silver handle and draw a distinct black one that reads long blade. From this handle, the metal leaves you draw should stretch out much further. These are elongated for reaching deep into engine blocks or tricky machinery where a standard leaf just can't reach. Finally, let's sketch gauge number 7. This one has a silver handle reading tapered, but instead of the standard rounded ends on the leaves, I want you to draw these leaves aggressively narrowing down to a very fine point. This tapered design is absolutely essential for slipping into the tightest, most awkwardly shaped corners where a wide, flat blade would totally just get hung up on the edges.
Moving on to Section 2, metric versus imperial systems, or what I like to call the Great Measurement Divide.
Now, what is really fascinating about this next pair of tools is how they look almost completely identical until you look at the crucial data printed right on their handles. Picture 2 standard fan-shaped gauges sitting side by side on our board. They've got the same basic silhouette as our very first classic gauge, but here is the critical difference for your blueprint. The metric version, we'll call it gauge number 4, proudly displays the text metric 0.02 to 1.00 millimeters etched right across its silver handle. It also features a matching silver pivot rivet holding the whole fan together. Okay, now draw gauge number 5 right next to it. This is the imperial version. Etch the words imperial 0.0015 to 0.025 inch onto its handle. And to instantly recognize it from all the way across the workbench, sketch in a distinct, solid black pivot dot holding the leaves together. It's such a brilliant, subtle visual cue that ensures a machinist grabs the exact right measurement system without even having to squint at the tiny numbers.
Okay, Section 3, double-ended and wire configurations. Let's look at some specialty shapes.
So the thing is, not all gaps are perfectly flat, right? And not all jobs require a single stack of blades. This brings us to some wildly different geometries. Let's mentally chart these out because their designs depart radically from everything we've sketched so far. Imagine gauge number 2, the double-ended gauge. It essentially looks like a rigid metal bow tie. You draw a central silver handle holding the middle, pinned down by 2 really distinct brass-colored rivets. From both the left and the right sides, a set of small, rounded metal leaves fan out symmetrically. This gives you a massive range of thicknesses in a very balanced, surprisingly compact tool.
Now, let's clear the board completely and sketch gauge number 6, the wire gauge. This tool ditches the flat metal blades entirely. Instead, draw a standard silver handle reading wire gauge. But radiating from the pivot point, you're going to sketch an array of thin, curved metal wire loops. Each of these fine wires is set securely into a striking, thick, gold-colored base where it connects to the pivot. Now, why wire? Well, if you're measuring the gap of a curved surface, like a spark plug in your car's engine, a flat blade just won't give you an accurate read. You literally need a cylindrical wire to truly measure that specific type of empty space.
And finally, Section 4, Next Level Precision. We're talking blocks and bytes.
For this final evolution, we are leaving the traditional folding fan design behind entirely, all for the sake of ultimate modern accuracy. I want you to envision a sleek, stark, black, rectangular storage box with a crystal-clear hinged lid. Inside this box, resting in perfectly molded slots, sit heavy, completely unattached rectangular metal blocks. This is gauge number 8, the Precision Feeler Gauge Setup. There is absolutely no handle. There is no pivot point. Honestly, it looks way more like a machinist's jewelry box than a standard hand tool. Each block is perfectly machined and vividly labeled with its thickness, ranging from a razor-thin .02 all the way up to a solid 1.0. Just, don't sneeze while holding that .02 block or you are literally never going to find it again. Because they aren't bound together by a rivet, they can be stacked or placed perfectly flat on an absolutely level surface. That offers a degree of rigid precision that a flimsy folding leaf just cannot match.
All right, finally, erase all of that and let's draw our very last tool, gauge number 9, the digital feeler gauge. We start with a silver handle and a traditional metal fan of leaves, but right at the pivot point, you need to sketch a chunky black digital housing. Draw 3 bright little buttons, off, on, and 0, and right smack in the center, a clear LCD screen. On that screen, glowing in crisp digital numbers write exactly 0.50 millimeters. This tool completely takes the guesswork out of feeling the drag of the blade. It combines the physical leaf slipping into the gap with a hyper-accurate digital readout, pretty much eliminating human error entirely from the equation.
So we've just sketched out an entire arsenal of precision on our mental whiteboard. We went from the classic stainless leaf to the specialized wire loop, all the way to the high-tech digital display. I really hope this explainer has successfully drawn these precision instruments in your mind's eye, showing you the absolutely incredible thought and engineering that goes into measuring literally nothing. It really leaves you to wonder, doesn't it? Just how perfectly calibrated is your own world, really? And the next time you need to measure the invisible, which one of these 9 incredible tools would you reach for first? Thanks so much for exploring this mental blueprint with me today. Keep asking questions and keep measuring the world around you.